Good morning, everybody. Welcome back to day 3 of our CubeSat Developers Workshop. It's good to see you all. As always, I want to give a big thank you to all of our sponsors. They really make this event possible to use this nice facility to enjoy the food and the networking dinner that we provide. Millennium Space Systems is our presenting sponsor this year. Blue Canyon is a gold sponsor. DHV and Maverick are both silver sponsors. And ULA is our bronze sponsor. So again, when you see them out there, thank them. They make this financially possible. I'd also like to thank all of the students. You've probably met a number of students from our CubeSat lab so far. They've been sitting at the registration desk. If you were presenting, you saw a number of them behind the stage. We work for basically starting in fall to put this together, and they put in a lot of time and effort, and they also really make this possible logistically. So I'd like to make sure we thank them, plus all the extra support staff that we get from here in the PAC and from on campus. It takes a big event. Yes, thank you very much. It takes a lot of work to put this on, and it's great to be appreciated. With that, I'd like to introduce our first speakers today. So we have Jack, Anthony, and Jamie. They're going to be talking about 3U Cubed, an IMAP student collaboration CubeSat software. So welcome the presenters.
Hello, everybody. Thank you for everyone that showed up for our presentation today. I know some of us would much rather be underneath the palm trees. I know I would. So this is the 3U Cubed again. Some people presented yesterday. This is more on the UNH side in progress. I'm Jack. I mainly focus on the OPC processing and air handling.
I'm Jamie. I work a lot on the electronic power system as well as ConOps.
And I'm Anthony. I mostly work on the payload and the instruments.
And thank you to everyone who's contributed to the project so far. So a brief introduction on what the project is about. It is a student collaboration which the goal in mind is to build and launch a 3U CubeSat, which is for the developing on hands-on research and experiencing for students. The actual goal of the CubeSat itself is to understand how Earth's thermosphere responds to particle precipitation and solar wind forcing and internal magnetospheric processes. The 3 universities involved are Sonoma State, Howard University, and University of New Hampshire. The overall spacecraft has 2 instruments, which has a combined size of 1.5 units and is commercially off-the-shelf subsystems for the spacecraft bus.
So our presentation will mostly focus on our engineering model. So as you can see, we have our main architecture here set up. You can see we have our central brain of the operation, the OBC. It runs on our EnduroSat framework. It communicates to all of our other subsystems, like our payload, our instruments, power, our EPS system, and most of it's through UART, except for EPS, which uses I²C. But first, let's just focus on our payload instruments. So our instrument, our payload, is mostly based on, it's all custom built. It's a homebrew. So we have our microcontroller and our 2 sensor units. We have our PMT, which collects ultraviolet light. We have ERPA, which collects data on energy distribution in space around it. And it sends, both of those sensors send data as analog outputs, voltage levels, over to our microcontroller, which we call the instrument microcontroller, the IMCU. So it has EDCs on it. It can take in voltage levels, and then with that data, it packetizes it, and then sends it over UART over to our onboard computer. So for our operation for our instrument, we have different modes that we used that basically does everything automatically. So our OBC can send commands over to our instrument, which puts in different modes. So like sync mode, it's our handshake, it syncs the RTC. It will send error counters, error packets, if there were any before a previous reboot or a system reset. We have our science mode, which is our basically main operational mode. It basically turns on the monitor power rails, it starts data collection, it starts a stream to then send out packets over to the OBC, so ERPA PMT packets. We also have housekeeping packets, which basically just monitor the health of our system. And then idle mode, it is basically the opposite of science mode. It turns off everything, halts data collection, just stops everything. And then we have a low power sleep mode, just to put our instruments into low power mode, just stops them. And then the OBC can send a command to wake up our instrument. So our interface with the OBC, we, as you can see, we have a breakdown of all of our packets. You can see each with how often they're sent, how big they are. But yeah, our OBC can interact with the instrument. Our instrument can interact with the OBC over UART. The OBC has single byte commands that can send over to the IMCU. So for example, a hex command would be like 0xA1, and that will tell the IMCU to go into science mode, and it will start data collection. And then idle mode would be like 0xA2. And there's a bunch of different other modes. We can disable and enable specific packets if we want to. Check specific rails. There's start a firmware update if we wanted to, but to test everything, there we go. We have our ground station equipment that uses a custom-based GUI, which we can just plug our IMCU into our PC. Over UART, it's like basically plugging into the OBC, but with just our personal computer. So this is how I mostly do testing and integrating. So you can see a picture of our GUI on the left. It displays live packet data, shows us a bunch of monitoring, voltage levels, sensor output, system statuses, and it's just a good way for me to validate and debug our firmware and just see what's up with our sensors.
So one of the parts of the satellite is the onboard computer, which is a commercial off-the-shelf EnduroSat. So the OBC itself, being EnduroSat, is equipped with a flight software which is built upon the EnduroSat's SDK, which is what we'll be using when the satellite launches. The OBC itself is responsible for managing and commanding and collecting telemetry, as well as onboard logging, file systems, and timing. The OBC itself is also the center of the satellite, pretty much. It is interfacing with all the subsystems, ranging from ADCs, EPS, and battery, to the transceiver. The onboard computer is also responsible for processing the data on board and saving it onto an SD card before it is downlinked. Some things to know is that the OBC itself has inter-thread communication and event-driven scheduling, and it also handles UART with interrupt limitations and buffering logic. So the OBC is responsible for actually processing the instrument packets that are sent from the IMCU. Like discussed earlier, one of the instruments is PMT, and we need 2 raw PMT samples to post-process 1 processed sample. The image to the right shows what the end-up processed packet looks like, and it is the result of just averaging 2 samples. The other instrument is ERPA, which has a little more complex processing. So we need 4 samples per sweep step to 1 post-process sample. And with 32 samples total, we get and averaged 8 sample for 1 per sweep step. The image to the right with the ERPA processing technique shows how the levels and the different packets work out to the different average samples. So for example, 1, 2, 31, and 32 would output to an ADC 0 and sweep 0 sequence. The processed instruments are also stored in corresponding buffers to overall reduce write times. And you can see the processed ERPA packet at the bottom. So the IMCU and OBC have error handling. So like Anthony discussed before, the IMCU can send and monitor voltages, temperatures to then generate an error packet if something doesn't look right. The OBC can then acknowledge that error packet and take the proper actions. This could be repowering instruments and other stuff. With error handling on the OBC can also involve the processed and collected data. Sequences aren't always showed up. They can be missing or corrupt. The image on the right shows a sequence missing the number 1. It goes from 0 to 3, so it is missing the second sequence, sequence number 1. And the image below that shows the correct one. So these missing packets are recorded in ranges to reduce write times and stored in missing files that can then be appended to the end. They are also flushed to help processing later for research.
So our satellites, CONOPS, or concept of operations, kind of just manages what the satellite does, how it does it, and when. You can see on the diagram there, it sort of just describes the different states that our onboard computer can go into. First is safe mode, which just happens when we either power up or under certain error circumstances. The detumble mode happens when satellite angular rates are above the acceptable threshold. Communications mode happens when the satellite is within range of our ground station. Science mode happens when the spacecraft is within the region of interest for us to collect the data. And idle mode is just the default mode. To manage smooth transitions between those, we also have some substates that we call commissioning modes. So CONOPS and commissioning modes are managed basically by comparing subsystem data against some predefined thresholds. The diagram here just goes more specifically into how those transitions work. But those thresholds include things like the angular rates of the satellite, geographic data, or the battery capacity. While developing on CONOPS, I've also implemented some features such as a system delay for the UHF transceiver and antenna initialization, which just prevents the satellite from transmitting before it's safe to do so. Another feature that I've implemented is a daily system-wide power cycle, which just keeps the software stable, basically by flushing any volatile memory. The other subsystem that I worked on a lot was the electrical power system. Ours, the EPS and the battery, was manufactured by ClydeSpace. We use the OBC to communicate with it via the I2C bus. So we can send it telecommands over I2C, which will either request data from the boards, or it will tell it to do things like toggling PDMs or the heater circuitry. We also get telemetry data back from it, which just allows the OBC to either monitor those systems, or it will make CONOPS decisions at runtime. So to fully integrate the EPS with our flight software, we needed a reliable way to have CONOPS interface between the hardware. So what I did was write a custom driver for the EPS on its own thread, which basically just constantly manages that communication. I also reworked the stock data caches that we got from EnduroSat, as well as the data handling for EPS, just to better support the hardware. So at runtime, what the OBC will do is it will periodically pull those boards and request basically all the EPS and battery data we can get from it. It will store all of that in the data caches. Those data caches will then be able to get read from any of the other subsystems. For example, ConOps will read the battery capacity and make decisions based on that. All of the EPS and battery data in the data caches will eventually get written to telemetry files, which will get downlinked to the ground station. And from the ground station, we'll be able to plot all of that data visually in near real time. But that is all we have for you. So thank you for coming. Are there any questions? I'm sorry, can you say that again? Yeah, so nearly the entire software package is written in C, though it's supported with some Python scripts, more so on ground station. Yes?
If and when your satellite resets, how do you prevent the commissioning mode from running again?
So we have two separate approaches to that we've still been working out which is better. But we have non-volatile memory on board the satellite, so stuff like ROM or the SD card, which we wouldn't use in this circumstance. But we can store which commissioning modes happened and when, as well as rechecking those same kind of thresholds to better decide where we should be based on where we have been. Any other questions? All right, well, thank you for coming.
Thank you, Jack, Anthony, and Jamie. Next up, we have Mike, Anuja, and Bridget from Princeton University presenting Princeton's experience in Max IQ STEM Launch Program to the ISS.
Okay, good morning, everyone. I'm Mike Galvin, and I'll be presenting Princeton's experience in Max IQ STEM Launch Program to the ISS. Clicker not working. Help. Okay, a little bit about me. My background was at Lockheed Martin Space Systems, but I've been at Princeton for the last 13 years as a research engineer and instructional staff. My day job is I work on like larger NASA missions, like the IMAP program, which I'm showing here. Princeton's leading this program, and in the last talk we heard a little bit about the program as well. That's on schedule for launch this fall. But I also help teach our spacecraft design courses, and then my favorite part of my job is I'm the PI of our TigerSat's student CubeSat program, which is why I'm here today. And then I have Anuja with me. Anuja's a star. She is the student lead of this particular project that we're presenting today. She's been in my TigerSats program for 3 years. She's finishing up her junior year. She's the treasurer of our great rocketry club. She's done internships at MTech Space Software in Greece, and this summer she'll be at Sierra Space in Colorado. But she'll be a senior next year, and she's already looking for her first full-time job, so I highly recommend you keep an eye out for her at the career fair today. Okay, so the context here is in 2018, I came to this conference for the first time, and I met the guys from Twig Space Lab, and I heard them talking about this ThinSat program run out of Virginia Space Consortium. And this was a program to try to get dozens of schools into space, into a free-flying orbit for the first time, all together on a batched launch. And it was all for Virginia, but I met them here and I begged them to allow Princeton into the program as an out-of-state participant, and amazingly, they let us in, and we had a great time with it. And I just left the program thinking it was just like a very beautifully architected program. And it was like a 3-phase program, which you're seeing here. The first phase was we got these STEM sensor and microcontroller electronics kits that were clicked together with no solder. These were provided by a company, MaxIQ, in South Africa, that generates STEM kits and STEM curriculums with a focus towards launch programs. And in that phase, you click them together, you learn some Arduino programming, you learn reading sensors, data analysis. You can make a ground station and a weather satellite, and you can do a little on-campus launch with a drone or a small balloon. Then you move to phase 2, and you're provided these 3D printed versions of ThinSats, which are like slice of bread size vehicles. And these were provided by Near Space Launch in Indiana. But you started with 3D printed versions that were functional in every respect, and you're allocated half of the ThinSat for some payload of your choosing. High schools or beginners would typically continue on with the kit payloads, and you could click those sensors right in and click them into the half of your ThinSat payload. But universities and more advanced teams could decide at this point to develop custom, more advanced experiments and integrate them in the 3D printed ThinSat. And these were simple enough that one of my students could build, design, test, qualify his ThinSat, which was this MEMSat, from his bedroom during COVID lockdown, which was really cool. And then the culmination of phase 2 is Near Space Launch would offer a batched high-altitude balloon launch into the stratosphere from their Indiana site. And that was effectively like a qualification of your system for moving on to phase 3, which was the orbital launch. In the orbital phase, Near Space Launch integrated all the experiments into a flight-qualified metal version of the ThinSat, batched them together into a CubeSat dispenser, and they were integrated onto one of the ISS resupply missions out of Wallops Island launch base. And they were actually injected into a very low Earth orbit, 200 kilometers. So they all have it's like dozens of these ThinSats, and they have a 1-week mission, which is really cool. And then they all burn up, create no space debris, which I think is just a fantastic model. So this will look familiar. This is what led us to this year's program from MaxIQ. After the ThinSat program kind of fizzled out a little bit, it had some manageability and reliability problems. We became very close with MaxIQ, who provides the kits, and we kept thinking, can we somehow reboot this program, but in a more like de-scoped, simpler, manageable way, where we can get a manageable cadence of batch launches for schools. So this is going to look very familiar. We start with the kits. In phase 2, you can integrate the kits into this, again, slice of bread sized flat format, where each school has about 1 centimeter of thickness to play with. You can keep using the kits, or at this stage, you can develop custom payloads. They get batched into this stacked platform, and then MaxIQ has relationships with NASA's Fort Sumner HAB launch base. So the batch launch gets on one of NASA's giant HAB balloons out of Fort Sumner for the qualification launch. Then we move on to the orbital phase, and this is where it changes a little bit. We're batching the slices of bread into a NanoRacks NanoLab, which is a CubeSat form factor, but it's designed to be stowed inside the ISS rather than deployed into a free-flying orbit. And that really helps with a lot of the reliability and manageability problems of manifesting these massive batched launches. So once we're stowed into this stacked format in a NanoLab, we're integrated into one of the modern ISS resupply launches, which is almost all SpaceX these days, on the way to be stowed in the ISS. And so the NanoLab's workflow is the NanoLabs arrive at the space station, they get handled by the astronauts, they get stowed into NanoRacks lockers, which get slid into racked cabinets in one of the ISS bays. And then the life cycle of a NanoLab it looks like here. You get launch, delivery. You usually get about 6 weeks of on-orbit operation in a true microgravity environment, orbiting at Mach 23 for 6 weeks, which is really neat. But what's really cool about our program is there are cargo return missions that will bring the nanolab back, and you can break it all back up, send all the experiments back to schools, even break up the experiments themselves and give them out kind of as trophies to students or mementos of a mission and their handiwork that really went to space. So that's retrieval and received back at NanoRex. So Princeton, we're actually customers of the program. We bought 3 slots on this year's launch. And you might be wondering, like, what are some interesting experiments that you can do in a environmentally controlled microgravity environment in the ISS? So Anuj is going to start by showing one of our experiments.
Yeah, so the experiment I've been working on, we have a variety of different sensors on there. So the first one is a custom PCB, which integrates a BME 280 sensor, and so that'll collect data like humidity, temperature, pressure. We're also planning on another custom PCB with an IMU on it. We have an accelerometer, which will collect 3-axis accelerometer data, acceleration data, a gas sensor, which will collect TVOC and CO2 data, and then finally we have a barometer, which will collect temperature and pressure data.
So Anuj is a junior, but her teammates are freshmen, and this is like a very nice freshman level payload where we're just using the kit to put together some environmental sensors and characterize our local environment in the stack itself. But sort of the reach aspect of this experiment, which Anuja took the reins of, is the opportunity to learn to design our own PCBs, namely in this case, designing our own version of an X chip, which is the kit component, to integrate into MaxIQ's ecosystem. And MaxIQ is super open and helpful with this, helping people make their own X chips to integrate into the ecosystem. So our next payload was also a freshman level payload. This was inspired by our 2021 ThinSat, which was Protosat. This mission was an attempt at to our knowledge, the first ever launch survivability of several different student-friendly PCB fabrication methods. We have a Volterra printed PCB, this is the Volterra tool, which is a PCB printer. It prints using conductive silver ink. We have a CNC milled circuit board, which might be familiar to a lot of students. And then we kind of have like a cheeky experiment here, which is literally just a simple solderless breadboard with jumper wires plugged into it with no staking, no glue, no nothing. And we're not forecasting that anybody's going to be using breadboards in their real flight qualified experiments. But we wanted to kind of do a reduction to absurdity thing of like really pushing the envelope of risk to see what could survive a Wallops Island launch. Unfortunately, the 2021 ThinSat launch had a systemic fleet-wide downlink failure, so we never got data back from this mission, so we decided to reboot it for this program. And so you can see here our payload down here has a Volterra printed circuit over here, a simple Adafruit solderless breadboard here, some simple environmental sensors just to serve as the canary in the coal mine as to whether the circuit boards are still working and have survived a violent launch to the ISS. Okay, then our next payload, we attracted one of our genius PhD students, electrical engineer, to the program also, and he designed his own mission. I am actually too dumb to understand how it works, so I have to read you directly from the email that he sent me explaining it. So this experiment implements a variable capacitor diode. When this diode moves at hypersonic speed through LEO's relatively stable magnetic field, the Lorentz force will narrow or widen its charge-depleted mid-region and thus its capacitance. So fine measurement of the capacitance of several specifically selected varactors moving at Mach 22 can serve as an orbital speedometer that depends on no external references other than Earth's magnetic field. And so we did a literature search. We think this device is novel, so we're very excited to see if it works on the ISS because it's actually, it actually can't work on the ground. It needs to be moving at hypersonic speeds to detect the velocity. We also have schools, colleges from South Africa in the program. This is Parklands College in South Africa. They're doing an inertial measurement unit, but they're reading it at a very high readout rate to try to serve as a vibration sensor. We heard in a talk yesterday that the ISS is a vibrationally noisy microgravity environment, and so we're trying to see some of that on a vibration sensor within the stack. Okay, and then you heard from Nipmuc High School yesterday on their HAB program, but Nipmuc is also participants in this program, and we have the fantastic Bridget here from Nipmuc to present their ISS experiment.
So hi, I'm Bridget. I've had the pleasure of working with MaxIQ and Mike Galvin for almost 2 years now. I'm a senior, but my final project before graduation is this ISS payload with 4 different sensors. The first 2 sensors are developed by MaxIQ, a weather sensor measuring temperature and humidity, and then an air quality sensor measuring carbon dioxide, hydrogen, ethanol, and volatile organic compounds. The last 2 sensors are a triple-axis magnetometer and a 9-axis gyroscope, accelerometer, and magnetometer. Both of these are developed by SparkFun and are attached to the payload using MaxIQ prototyping chips. And then for the programming side of things, we took advantage of MaxIQ's dual-core functionality, and we have 2 tasks running separately on each core. The task on core 1 handles the data collection from the MaxIQ chips, and as well as storing all the data to the SD card. The task on core 0 only handles the data collection from the SparkFun chips, allowing the data collection to happen as fast as possible from those 2 sensors. And we're currently in the process of testing everything and super excited to see the payload fly.
Thanks, Bridget. Okay, real quick, one thing I love about the NanoRacks platform is there are real requirements. And these requirements you can flow down to student teams and schools and get them working in a real systems engineering framework, like real engineers, rather than kind of designing things willy-nilly at a student level. So the NanoRacks platform has an interface definition document, and all the experiments within the stack have to comply with NASA's standard material and processes requirements, as well as NASA's flammability, off-gassing, and compatibility requirements. So this is just a really nice context to get students working in a real engineering environment with real flowed-down requirements. But if you have requirements, you have environments. For example, we have a random environment and a random vibration environment from the IDD here. And if you have a vibration environment, of course, you have to do a vibe test. So my lab has a little shaker table from right here in California, LabWorks. So we could do vibration testing of Princeton's payloads. And then my lab also specializes in DIY qualification testing. So we've designed our own little shaker table, motorized. We've designed a thermal vacuum bell jar that works, it's just right size for 1U CubeSats. And then I have a 10E thermal cycling. And so that's out of Cape Canaveral. This is not part of the stock program, but you know if you have a launch going out of Cape Canaveral, it's like a really great opportunity to take your students to the KSC Visitor Center, which if anyone's been there is like a national treasure. It's like a great visit for your students and is like a really nice culmination to this year-long program. I talked a little bit about the life cycle of NanoLab. Again, like the secret sauce of this mission is the unique return phase, which we think is going to be really cool. And then what about the bottom line? So MaxIQ is hoping to reboot this program as soon as next year, as soon as starting next school year. And this is the cost of enrollment for a school or a classroom or a club. And what I can say is, from my knowledge, this is the cheapest ticket to real orbit in the world that I know of. And if there was a cheaper ticket to space for your CubeSat program, I would have just bought it. I wouldn't have spent all this time helping to plan this program. So $15,000 gets you into the program, and it includes not just the launches, but a whole curriculum. It includes all the kits for your whole club, for your whole classroom. It's paid in 2 installments. You can pay $6,000 up front, and that gets you all the no-solder, click-together electronics kits. It gets you a furnished curriculum, tutorials, and a series of live MaxIQ-hosted Zoom workshops. And that first installment payment also includes the HAB launch. And then if you're ready, the second installment payment, $9,000, that gets you manifested on the ISS launch and gets you the return of your payload also back to your school. And the program's great for middle school and high school programs, but you can see it's also adaptable to universities who want to design more advanced payloads. And I just find it's really good for beginning CubeSat programs who are just intimidated by looking at a blank sheet of paper or the steep cost of CubeSat COTS subsystems. It's also really good for mature CubeSat programs that want to have an onboarding program for their new freshman members. You kind of accidentally learn CubeSat design skills when you get through this program because you have to design this stack of circuit boards and learn sensor readout microcontrollers and PCB design. And by the time you've designed a NanoLab stack, you've learned to design a CubeSat as well. I think that's all I have. So here's contact information for myself, for my lab, and this QR code will take anyone to the program page at MaxIQ's website where you can learn more about the program and you can directly sign up for the year 2 cycle if you're interested. We'll be participating, Princeton will be participating again. We're having a few return schools to the next program and we're looking to enroll enough new schools to do another ISS launch. That's it. Okay, any questions? Anyone interested? It's quite the opposite. So MaxIQ is based in South Africa, and they're very invested in enrolling schools in Africa. So I didn't show it, but this is the last year's balloon launch, and we have schools from Massachusetts, Ivory Coast, Georgia, Cameroon, South Africa. We're very invested in the international community. So yeah, we're accepting schools worldwide. And the question was, is this open to international schools?
The early bird pricing timeframe, when do schools kind of have to commit for that pricing?
I think that price will be active through the summer. And then MaxIQ is very flexible, so just talk to them. But yeah, I think the pricing will be active through the summer. Any other questions? Oh, yeah.
Do you do any flight tests on site at Princeton?
Yeah, so I showed, we have like a range of capabilities. I had a student design, so most vibe shakers are electrodynamic shakers. They're like giant subwoofers. Most of them are huge. They cost hundreds of thousands of dollars. So we wanted to develop a range of our own vibration test capabilities. So I had a student design a motorized shaker. This is just a giant high torque stepper motor that can jitter this linear stage back and forth. And if you move your test article around 3 axes, you can do a 3-axis sinusoidal vibration test. You can't do random vibration with obviously a reciprocating motor. But sinusoidal testing, you can test for resonances, and you can sweep through like 0 to 100 hertz to check if your system has any low frequency resonances to destroy itself. And then at like mid-sized payloads, which for us mid-size is like a 1U CubeSat. So on this you can test thin sats or circuit boards that are going to be in your CubeSat stack. But for like a full 1U CubeSat, we bought this LabWorks shaker. This is off the shelf. This is actually a CubeSat kit from LabWorks, and it's fantastic. It's I think they're selling it. It's about $20,000. So that's a lot of money, but it's obviously within Princeton's striking distance. And it's spec'd to provide NASA GEVs, full NASA GEVs qualification levels for a 1U CubeSat, and then you can use it for subsystems and everything also. And we've just had a lot of fun with it this semester. We've been shaking everything we can get our hands on this semester, including this is Anuja's payload that she presented. We're going to try to shake all of our ISS payloads. And then for things larger than 1U, there are some local environmental test facilities in New Jersey that we pay them a few $100s, and they let us come in for a 2-hour test of just 3 axes for 2 minutes each. So yeah. But yeah, I have a little time, so we have we're a mechanical engineering program. CubeSats are frustratingly an electronics project. We design terrible circuit boards, ugly circuit boards. we just learn the bare minimum of electronics we need to give us excuses to do mechanical projects. And ground qualification testing is a very rich mechanical challenge that I think is really overlooked by a lot of CubeSat programs that outsource the qual testing. Whereas if you're trying to start a CubeSat program, but you don't have money to pay for a launch, you don't have money to pay for a lot of flight qualified components, there are a lot of rich single semester, 2-semester projects in developing and using your own ground qualification test equipment. So I'm just showing a small bit of it here, but yeah, we designed our own thermal vacuum chamber that uses no cryogens. When you get down to a CubeSat level of components, you can actually cool them with just thermoelectric Peltier coolers. You don't need cryogens to get like a PC104 circuit board down to -20 or -30 C. You can do it with a little Peltier cooler. And the Peltier coolers are reversible, so you can put a little Peltier cooler in a classroom bell jar, and you can heat and cool your experiment to NASA GEVS levels. It works okay. There's a lot of waste heat coming out of Peltier cooler, so far what we can do is we can cool once down to NASA levels, and then we have no problem heating up once because we have just a ton of waste heat, but then we have trouble getting back down to cold for the next cycle. But we're working on this. Our next iteration, we're going to try to use off-the-shelf refrigerants while still trying to avoid the safety implications of using cryogens with students. And then, yeah, my 10E cycling chamber, I had a little extra money one year. I bought this for $1,000 on eBay, and I'm spending this summer trying to figure out if it works or not. So that'll be for larger payloads. But yeah, we do a ton of ground qualification projects with our students, which cost nothing compared to launch programs. And it's a really good way for students to feel that they're involved in a real space program, but it's not the pressure of leading to a real manifested launch date and the real budget implications of that. So, any other questions? I might have 1 minute left. Yep.
Do you have a single-sided A4 with the parts you use for that?
I'm sorry, can you say again?
Did somebody bother to write up your inexpensive thermal vacuum?
Oh yeah, we have a paper. So I try not to. I like to get people to have to email me. So there's a splash page on my TigerSats Princeton website about this project, but there's a 30-page paper about the design and build and test of it, and I'd be glad to provide it if you respect my request to email. Yeah, and the question was, is there an open source design and parts list for this thermal vacuum chamber? I think I'm done. Thanks, everyone.
Thank you, Mike, Anuja, and Bridget. Next up, we have Daniel Freeberg from Illinois State University, presenting From the Ground Up.
Hello, I'm Daniel Freeberg. I'm from the School of IT at Illinois State University. My co-presenters on this project that aren't here today are Dr. Will Lewis, also from the School of IT, our Chief Information Officer, Charles Edamala, and our aerospace engineering expertise on this is Dr. Lembeck from the University of Illinois. And our presentation is entitled, From the Ground Station Up, Space IT Education via Operation and Management of an S-band UHF VHF CubeSat ground station. In today's presentation, I'll be talking about starting a CubeSat program with the ground station, and then how at Illinois State University we plan to use our ground station to introduce students to space IT. Also then, I'll give you guys the ground station location and specs, and then I'll talk a little bit about why we're here, and that's to announce that we have a S-band UHF VHF ground station as a service, and we're here seeking collaborations. Then I'll have time for questions, and I'll have my email address up there to contact us. So Illinois State University, we do not currently have an aerospace engineering program. We are excited that our College of Engineering is starting next fall, next semester. And our College of Engineering will have electrical, mechanical, and general engineering majors. Currently, Dr. Lewis and I, we're in the School of IT at Illinois State University, and 2019, about 5-6 years ago, we started researching, can a university without an aerospace engineering program develop and launch a CubeSat? We started with a feasibility study, and we concluded that since we could purchase a CubeSat, in 2019 we could get online and purchase a CubeSat, much like today, that we really didn't need an aerospace engineering discipline or faculty or a lab to develop a CubeSat. We could just get online and purchase it. But we also concluded that a program like that would be best supported with a College of Engineering. 2 years later, our university announced that our College of Engineering would be starting in fall 2025. So we were real excited. We continued our research. I surveyed about a dozen different universities that had started CubeSat programs, and to figure out what type of expertise, how many students are involved. One thing I've learned that I thought was interesting from those programs was universities that had launched one CubeSat but hadn't launched another all stated, I wish we could launch another CubeSat. Students really liked it, really wanted to do that. So at ISU, we kind of started thinking we don't want to get into that category. So rather than just develop a CubeSat, we want to develop a CubeSat program. So that every 3 or 4 years, we're building and launching a CubeSat and or supporting a CubeSat program with our ground station. Dr. Lewis and I also began looking at, when we first started, we had no engineering there, so we looked at the IT aspects. And then we first built a small UHF ground station, much like ones that have been presented here this year and last year, just a Yagi antenna, UHF antenna. We started downlinking from AMSAT satellites, AO91, AO88 when it was available, FunCube, and just learning about downlink times, passes, and from there the university decided, before we decided that, when we were doing our feasibility study, Illinois State University is about 45 minutes from the University of Illinois. The University of Illinois has a laboratory for advanced space systems, and that's where we met Dr. Lembeck. And Dr. Lembeck talked to Dr. Lewis and I about getting another university in Illinois involved in space technologies. So what we first did was have some of our students work with some activities along with the University of Illinois, and we participated in a vertical landing rocket competition for 3 semesters. Our students and the U of I students, Purdue students, and I think Southern Illinois tried landing rockets instead of launching them. Our students found that to be exciting, challenging, fun. So we learned that even, not just aerospace engineering people find that exciting, IT students found that exciting too. So ISU then decided what we're going to do is we're going to upgrade the ground station to an S-band UHF VHF ground station, and will support universities with CubeSat missions. That will give us a little bit of expertise in learning how to develop CubeSats, especially without aerospace engineering faculty at our university. While we gain experience, we plan on using our ground station in our School of IT and also in our electrical and engineering school. What we're trying to do is expand our IT education to include space IT education. Currently, our IT is focused on like land-based systems, mobile networks, mobile communications networks. And we want to expand that to include space IT. So right now we have networking, cybersecurity, computer science, and information systems. So in our networking, we want to get our students not just looking at land-based systems and mobile networking. We want them to look at some space communications, ground station network, and then also space communication protocols. Our cybersecurity students, we want them to learn not just only to secure land-based systems and mobile networks, but to learn the importance of securing space networks. I think we had a presentation yesterday from Cal Poly talking about cybersecurity in space. Last summer, I attended an IEEE Space Missions Challenge conference for IT and computing, and one of the themes at that conference was currently we have aerospace engineering experts and we have cybersecurity experts, but we don't have space cybersecurity experts. So we want to get our students looking at that. We think by getting them operating the ground station, possibly working alongside universities, building their CubeSats, they'll learn the importance of securing space systems. Currently, our faculty is working on a low-power encryption study. We're trying to identify which encryption methods on CubeSats would consume the less power, and we're planning on publishing that paper, I think, this year. In our computer science classes, we want to introduce our students to satellite tracking software and then software-defined radios. And then our information system students, we want to introduce them to telemetry data, managing the downlink data, and then possibly again having our computer science and IS students working on creating some AI algorithms to analyze the telemetry data and then predict future telemetry. So here's our ground station specs. We'll have 2 rotators, 2 antennas. One antenna will be the UHF, VHF, both cross joggies. The UHF will be 395 to 405 megahertz. The VHF will be 144 to 146 megahertz. And then on a separate antenna will be a an S-band 3-meter dish at 219 gigahertz to 229 gigahertz. I skipped a slide. Okay. Here is where our ground station will be located. The red dash up there is where Illinois State is located, right in the middle of Illinois. We think our ground station has a great location, especially for universities on the coasts. By collaborating with us, we can extend your network to include a ground station right in the center of the country. The insert over there is our current progress on our installation. We first wanted to put our antennas atop one of the dormitories. We got a little pushback on that, so then we looked out at one of our university farms. So about 18 miles off of campus. I call it out in the middle of nowhere. If you're in Illinois, it's real flat out there. It's out in the middle of acres of farm ground and completely flat. Right next to where the ground's being prepared is a module classroom out there. So what we're going to, that'll house the software-defined radio and servers. So what we'll do on the prepared ground, we're going to put like a container, like a shipping container, and atop that we'll put a platform with the 2 antennas. So we'll get up above the building, and then we'll have 360 unobstructed view there. From there, I think we got fiber optic cable back into the university. And like I said, the important announcement is we're here to announce and present at the conference that we want to use our ground station to support universities and or other entities that have CubeSat missions. We kind of envisioning about 4 different levels of collaboration, one being commercial, where we would provide full ground station support for your mission. Another being like a research type collaboration where if we're allowed to work right alongside your students and your program so we can learn expertise on building a CubeSat and or maybe possibly put a board on your CubeSat. That would be a level of collaboration. We're also looking at using our ground station as like an educational tool for other universities. University of Illinois has been extremely helpful in getting us to where we're at today, starting from nothing. And we have found it to be exciting. We're real excited to be here today. So we want to help other universities that maybe think, they don't have a CubeSat program. They think space technologies is it's an overwhelming, they cannot do that. We want to be able to, show our ground station, show our program, show our collaborations, and let universities know, no, it is possible. And then finally, we want to use our ground station for some community outreach so our students, undergraduate and graduate students, can go into high schools and community colleges and talk to those students about CubeSats and downlinks and passes and stuff like that. Our pricing, so our policy now is we don't have prices yet because we're not up and running, but our policy was we'll have our ground station at below commercial rates, and then the rates will also depend upon the level of collaboration. So if it's the full scale commercial, we're supporting your entire mission, doing everything, it would be at the full rate. It would be at a reduced rate if we're partners with you on a CubeSat mission. And we envision our ground station to be used as a primary ground station, also can be used as a second ground station to extend your downlink time, or as a backup ground station. So I got here a week before I got here, I just learned that both crates had arrived to ISU. And you saw the picture of the ground being leveled. I think next we'll get the container put in, and then by midsummer, the ground station will be assembled, and we can begin operations. We're currently planning to support missions starting in 2026. And we expect our ground station to be operational for at least 10 years. So if you found that to be at all helpful, possibly in the future to support one of your missions, my name's Daniel Freeberg. I'm at the School of IT. It's my email address up there. And that was probably quick. Was that too quick? I got questions, comments? Yes.
Your ground station, you talked about maybe putting on one of the dorm buildings.
Yes.
And you went out to the farm. Probably a very good move because of the noise level and within the campus. We found out with some of the universities we worked with that if the ground station is on the campus, you've got all sorts of noise from several different places.
Okay. All right. If people didn't hear that, it's told the location at the farm is an ideal location for a ground station. Yes. No, we'll support anyone with a CubeSat mission. So I said universities because we're here, but we also have, I think, some military academies that we would support, and or I think, yeah. Yes. Yeah, we believe so. We believe so, like the lead time up to, like if we know we're going to support your CubeSat, we would be able to, get the appropriate software so that we can decode the downlink, yes. So that, so right now we don't have that problem because we only have, I think, one mission. But yeah, we'd have to figure that out. If we had 2 or 3 missions, hopefully we would have different pastimes. But yeah, if we were to support 2 or 3 missions, it could be a problem if they're both passing at the same time. So, yeah. Yeah.
Your UHF antenna coverage, what was that frequency range you were calling?
I think 395 to 405.
And of course, looking at it from the amateur radio point of view, is that a band that's available on the EnduroSat radios or something like that?
It's the band that the mission that we're currently supporting is using. I think the other band's a 430 band.
Yeah, well, you get into the amateur at 430, and then at 437 is a lot of the experimental licensed satellite traffic, as well as in the 430 to 435 is more or less AMSAT type stuff. That's why I was curious.
So yeah, we purchased this to support our first mission. We have talked about having a 430 that we could just put, take the 395, 405 off of the rotator and then put the 430 on to support other missions too.
Yeah, that might be something we get some collaboration with other schools and such in that vein.
Thanks. Any other questions? Yes. So we purchased the entire kit. When we started looking at this 2 years ago, we didn't want to piece it out. You could piece it out for a lot less than we bought it for. We bought 2 servers, I think 2 SDRs, 2 rotators, and then the antennas for, I think it was about 100,000. So we thought relatively cheap for a university to get into space technologies, but still, it could be a lot less than that if a person could just buy the antenna and probably build the rotator and everything themselves, and then use an old server or an SDR. Any other questions? Yes, yeah.
Building up our ground station before CubeSat, and we started out with using a 915 megahertz band, but we want to support other missions in the future, so we're looking for that 430 upgrade. So I think you get a lot more like cross collaboration if you do that 430 megahertz range as a potential upgrade for the future.
Thanks. Okay, that's it. All right, thanks guys for your time. I got the stop sign. All right.
Thank you very much. Our next presenters will be Colin Riddle, Micah Wilson, and Josh Engler. They'll be telling us about advancing undergraduate space research with a standardized CubeSat bus. Please welcome the presenters.
All right, good morning, ladies and gentlemen. Thank you for having us. My name is Colin Riddle. Midshipman Josh Engler, Midshipman Michael Wilson, and I are here from the Naval Academy Small Satellite Program to share with you some of the work that we've done on developing an affordable, flexible, universal standard bus for CubeSats. A little bit about us. The Naval Academy Small Sat Program is 26 years old, and we've launched 19 payloads over those years. 9 of those have been CubeSats. For the past few years, we focused on this project in order to enable both our team and those of other researchers to rapidly develop and deploy experimental payloads. As all of us know, having worked on CubeSats, there are a lot of major obstacles that you go through when you want to kickstart a small sat program. So number one, CubeSats are really expensive. The average cost for a CubeSat mission for a university is around $500,000, and that's with a development time of 3 years. CubeSats are almost entirely custom made. So when you build a CubeSat, some industry standards developed by companies like PyCubed and Pumpkin have made it easier. But a lot of your modules, such as your payload interface and your command, and really anything that you don't buy directly from these vendors, has to be entirely redesigned for each CubeSat mission. And some of the industry has tried to alleviate this problem through the use of standardized modular components. But while these are really helpful in designing your bus, due to that payload interface module, they really turn the satellite into one-off custom things that are one flight, and then you have to completely redesign your next satellite. And lastly, CubeSats are just really hard. There are a lot of compounding risk factors when you build a satellite, and that results in when you deploy your satellite, no matter how well a job your team has done, you don't know whether or not that satellite's going to come online. This is RSat-1. It was our capstone project from 2017 that we intended to test the feasibility of robotic arms and satellite repair. Despite our best efforts, it never came online. Stories like these are all too common, and we want to alleviate that issue through eliminating the risk factor of developing a bus every time that you develop a satellite.
So the Naval Academy Standard Bus aims to solve all of these problems at once by providing a standardized and consistent bus for payloads. So by standardizing the delivery of payloads, we aim to make it easier for universities and research groups to focus on the end goals of their missions, primarily getting data down from space. As it stands currently, a lot of time and resources that could be used to develop experiments and procedures are being used to solve problems every time you rebuild a satellite on command and data handling that have already been solved. So the Naval Academy Standard Bus can be thought of as a semi-truck or a tractor trailer capable of transporting payloads of different sizes, shipping containers of different sizes. So because of the standardized nature of a shipping container, mostly due to the mounting hardware on the container and that same standard being matched on the truck that's doing the transporting, payloads of different sizes carrying different things can be transported without the need to any modification to the actual shipping container or the truck doing the transporting. So much like that truck, our standard bus can be flown independently, or it can host a 1U or a 2U payload module.
The Naval Academy Standard Bus can be produced quickly, and with proper documentation requires few technical skills to assemble. A 1U bus, and trust us, we've done this, can be assembled with just the necessary components and a little bit of soldering skill. Keeping with the tractor-trailer analogy, once a 2U payload module has been built, a simple 10-pin connector can be routed from the 2U payload to the 1U bus to form the 3U satellite. This is similar to how a tractor and trailer can be integrated to form the full semi-truck. And because the standard bus is, well, standardized, payloads can be rapidly integrated and launched. This greatly reduces development time, reduces integration time, and less wait time for you to get your data from space.
This is a quick overview of the conceptual design of the standard bus. As you can see, it is really only 5 boards that pass power and serial data. All in all, the entire bus, including the 1U bus itself, the 2U payload module, the solar panels, and all hardware excluding the actual payloads themselves, costs only $6,500. So speaking of that payload module, here it is. It just provides structure and power to the payloads that we will fly on each standard bus. So we'll provide a payload interface board to every payload manufacturer, and then as long as it fits, it can fly. Right. So while we would love to go crazy with the payloads that we can fly, at the end of the day, this is still a CubeSat. So there are some dimensions that we are working with, particularly in the mechanical and electrical interfaces.
So let's first talk about the standard bus's mechanical interface. As you can see here, the payload module must be mechanically fastened to the standard bus. Luckily, the connection point we designed is pretty simple. As you can see here, there's two concentric cylinders that slide from the payload to the bus to prevent the bus and payload from moving apart from each other in the X and Y direction. With just two screws, the payload module is also prevented from moving away from the bus in the Z direction. As you can see, this is the fully assembled satellite, and it acts as one cohesive unit after it has been mechanically interfaced with the payload and the bus. Here is a mechanical render of the bus being assembled. As you can see, after the bus is assembled, the concentric cylinders slide together, and with just two screws, the satellite is fully mechanically integrated.
Let's talk now about the electrical interface. So going back again to the analogy of a tractor trailer, the shipping container cannot just be mechanically fastened to the truck that's pulling it. There would be no brake lights, and that would just be a wreck waiting to happen. So we provide a PIB to each payload manufacturer such that the necessary connections can be designed and built for. And here's what that looks like. The PIB is really, really simple. At its heart, it's just a serial multiplexer. RX, TX, and power come in from the bus, are switched by an Adafruit feather, and then passed on to the payloads. And then in reverse, data comes from the payloads, is switched by the feather, and is passed on to the bus. So it really is just one 10-pin connector. It's that easy. And here's what it looks like when it's actually fabricated. As you can see, once again, a 10-pin connector comes in from the bus. There's the feather, and then there's one header for each payload.
And now, on to how we're actually going to use this thing. USNA 16, launching in December of this year, is our first planned mission to implement the Naval Academy standard bus. The standard bus will accompany two payloads from our partner schools, the University of Maryland and the United States Air Force Academy, on a low Earth orbit with an altitude of 500 kilometers and an inclination of 60 degrees. This ride-sharing capability is something that we really want to emphasize when presenting this to you, because we can have multiple payloads from different partners going up on one mission, making this a huge collaborative effort. This specific satellite will have 4 side panel coverage, allowing us to have a mission life of 2 years. So integrating your payload with our Naval Academy standard bus is really easy. We have this cutout on the positive X side of the board, and then the corner holes follow that used by pumpkin PCBs, which has become sort of a standard for the small sat industry. And so using that, both of our teams were easily able to integrate with our payload. UMD's payload is a test of their own ultra-high frequency communications and antenna deployment system, and it'll operate their own antenna using our power. So the cool thing about this is that it'll demonstrate the fact that we can operate an entirely independent payload despite supplying power to it. So all communications from UMD go directly to their own ground station with no middleman involved. Air Force's payload is a dosimeter that'll measure radiation in the South Atlantic anomaly. This is actually the Falcon Rad dosimeter that was presented to you by that fine gentleman over there in the blue suit yesterday. So the South Atlantic anomaly is a region of higher radiation that's caused by an offset between Earth's rotational axis and its magnetic field. And what this is going to do, it's going to demonstrate the fact that we can relay navigational data from our satellite to our payloads and tell them when to collect data if they have a position of particular interest. So when it flies over the anomaly, the Naval Academy bus will tell their board to collect data, and then we'll handle the data and give it to them. So it's a big collaboration between ourselves and Air Force. It really cements that partnership that we have, but still, beat Air Force. So USNA 16 only has 2 payloads on board, and as we stated earlier, we can accommodate up to 3. And so in the absence of a third, we make a dummy weight to sort of keep an expected center of mass for the whole satellite. This dummy weight is carved from aluminum. It's super easy. We do it in our own shop, and it's calibrated to each individual payload module in order to keep that expected center of mass.
Initially, the standard bus project was developed for senior capstone students to learn about the process of sending a satellite to space. This project is a great opportunity for aerospace and astroengineering students to learn the mission design process and gain valuable leadership and organizational skills that we all hope to use one day when we commission in the Navy or Marine Corps. However, with seniors only having 1 semester to plan the mission and design the satellite and 1 semester to build, we've decided to open this up as an extracurricular opportunity for the entire brigade of midshipmen. This will allow information to be passed down from class to class to allow for more iterative design and better collaboration as we move forward on future satellites. With the goal of eventually creating a design document with all the necessary instructions, parts, and assembly requirements to build the Naval Academy standard bus, we are currently undergoing some design changes before our flight later this year. We are standardizing connections within the bus. We are undergoing some shape changes for easier fit and assembly, as well as optimizing the bus for better power efficiency.
All right, thank you very much for having us. Thank you to our faculty advisor, Dr. Kang, for the wonderful help that he's provided us over the entire course of this project. Are there any questions? Yeah, go ahead.
So within the launch vehicle that we're sending the satellite up in, it's not actually necessary to fasten the payload to the bus. It's just kind of so they act as a cohesive unit in space. Recently, we have done a vibration test, and it went well. And then a couple of our students, I believe, have done some simulation as well. So I hope, does that answer your question?
So I'd say the biggest difference is cost. With commercial off-the-shelf things that you can buy, a lot of those are running you tens or hundreds of thousands of dollars, like ADCS modules, all of that. What we're offering is a $6,500 bus that we can build, and then you can design your payload, and we just slap it on and fly it. Does that answer your question?
So really that's up, sorry, the question was, like, if we could illuminate a little bit about the timeline of working with another university or another research group in order to implement their payload. That's really payload dependent. So, for example, with the dosimeter, it's kind of a one major component, one circuit board payload. So working with you, it was really easy just to kind of cut that slit into the side, put our template connection in, and be done with it. But more complicated payloads might require more time. Less complicated would require less. It really depends. We love working with people, so just talk to us and we can figure it out. Anything else? Over there? So our current plan, the question was, if this is a standardized asset, do we plan to release this as open source? Currently, our plan is to build our own stockpile of them and then work with other research groups on a case-by-case basis. What we're offering is essentially a ride with our missions to anyone who would want to implement a payload rapidly. Does that answer your question? Yes, ma'am? So the question was, what's the future of this project? What we're doing here is essentially allowing ourselves to go crazy with payloads. Since we've wanted to do all these missions, like I mentioned RSAT before, testing out the robotic arms on a CubeSat, which is really cool, but it was a failure due to having to redesign that bus. So what we're doing is we're taking care of that part. We intend on building a massive stockpile of these standard buses. We're going to use them as a project to teach new students. So we're developing these buses, building them over and over, testing them, and then once we're sure that they're good to go, we just go crazy with our payload designs, and we can really accommodate anything on those. So it's less that we're going to keep improving the bus, although we will be doing that a little bit. It's more that we're using this to launch other projects. Does that answer your question? Yes, sir.
So right now the bus is, the question was, can we accommodate larger than just a 1U or 2U payload? Right now the bus is only built as a 1U unit. So we can accommodate anything that fits with that 1U. And then it can extend higher than 2U. But right now we can't accommodate anything wider than a 1U base. Does that answer your question?
Mind if I add to that?
Go for it.
With USA 21, which our firsties presented to you earlier. 18, sorry. We are planning on doing a 3x1 payload, which is extending from the 2U that we've done before. So we are capable of adapting those, I won't say bigger, but longer payloads, and we'd love to try more if you have something for us.
Well, if there's no other questions, we'd like to thank all of you for having us. And if you have any other questions, you can find us out in the lobby. Thank you.
Thank you to the United States Naval Academy. Next up, I'm excited to announce Dylan Hall, Lauren Sorsey, Brendan Lyle, Porter Banks, and Caden Wang from Oakwood School presenting Technology Development and Educational Outreach, Oakwood High School's NeonSat mission.
Hello, everyone. My name is Dylan Hall, and I'm the structure lead of NeonSat. We're a team of high school students from Oakwood School in Morgan Hill, California. I'm joined today by all the other leads of the NeonSat mission. We currently have 15 students working on the project, but there have been about 35 of us since the project began. We are here today to talk about the NeonSat mission. NeonSat is a 2U CubeSat. Our satellite will inspire students and provide learning opportunities while contributing to the development of new and innovative space technologies. We've tried to put together a very ambitious project. Rather than relying on commercial off-the-shelf products, we're doing this ourselves to learn as much as we possibly can. Large portions of our satellite will be fabricated and designed in-house. We were recently selected by Call 15 of NASA's CubeSat launch initiative. We were the only high school selected this cycle among many other great colleges and universities. We have 7 payloads. We're going to tell you about a few. There's 3 categories of payloads. Our first is technology demonstration. This is our acoustic spacecraft mapping and sounding payload, our orbit determination of other small sats, which will use radio to talk to other, communicate with other satellites in their orbit and possibly determine their status. Our cryptographic ledgers in space payload, LCVR waveform generator, and then for our educational outreach payloads, we have our shooting star dispenser and a camera, and then we also have some science and outreach, which is our material science experiment.
Our acoustic spacecraft mapping and sounding payload uses solenoids to tap against the spacecraft structure. while ultrasonic microphones listened for the resulting vibrations. By analyzing these vibrations, we believe that we can gain insight into the status of the satellite. We hope that this method will be especially useful for monitoring deployables, like antennas or solar panels, helping confirm whether they fully deployed without relying on physical switches that can fail or add complexity. For this mission, all of the analysis is going to take place on the ground segment. We will excite the structure and record vibrations, and send the recordings to the ground. We have been using autocorrelation and cross-correlation on this data from our piezoelectric sensors to characterize changes in structure and deployment. Beyond small satellites, this approach could scale to larger missions. For example, it could help estimate fuel levels in a tank by tracking how sound waves propagate through liquid and structure. It could even be used to map the structure of another spacecraft or asteroid through acoustic sounding. It's an innovative way to get more information about what's going on inside of a vehicle and has the potential to improve reliability across many mission types. Also, if you haven't had the chance to yet, be sure to check out our poster in the poster track for more information. We also have educational outreach payloads. One of these payloads is a material science experiment designed to study how various semiconductor devices behave when exposed to harsh conditions of space. These components will be mounted externally, where they'll face radiation, extreme temperatures, and vacuum over time. But this payload isn't just about the data. It's also about educational outreach. We're sending kits to disadvantaged schools across the country, allowing students to run control experiments on the same semiconductor types that we're flying. They'll be able to follow along with our results, make comparisons, and engage with real space science in an engaging way. Our other outreach payload is the Shooting Star Dispenser. We're partnering with elementary schools in our local area to collect student drawings, which we're printing onto a long ribbon and flying in space. Once in orbit, the ribbon will be dispensed, symbolically releasing their creativity into space, which will eventually burn up upon re-entry, creating a small shooting star. We're also taking orbital debris concerns seriously. The dispenser is being carefully designed to release the ribbon in a way that minimizes risk and fully complies with debris mitigation standards. It's a fun and meaningful way to connect with young students in a space-related engineering project, giving them a real role in our mission.
Once our satellite is released into space, we will wait 45 minutes. We will then deploy our antennas and attempt to detumble. We'll then await ground commands. Some of our early actions will be the control observations from our acoustic payload before further deployment. Overall, our approach is to avoid processing a lot of data on the satellite. Experiment data will be downlinked in raw form to give us the maximal flexibility. This creates the need for a lot of downlink data. We've chosen to go with 4800 baud data to maximize link budget. Because of this, scheduling downlinks when there are other ground stations listening becomes very important. We're a part of the SatNogs network that allows us to use ground stations around the globe. We're developing our own structure and machining it in-house. Our design features 2 rail pieces connected by 4 center braces. This allows us to have 0 broken rail space aside from our deployment switches, and it means that we meet all dispenser requirements. This improves our chances of getting a launch opportunity. We're using a 3-axis gantry milling machine to fabricate the structure. Unfortunately, we do have a Z height limitation, but our separation mechanism and deployable solar panels have been designed around this. We're also custom thread milling for polygonal deformation helicoils, which will enhance fastener retention. We also have a machining fixture that will help us machine the center braces of our satellite. You can see here. And we're also working with some local firms, Phoenix DevVentures, which is providing a clean room for final assembly, and MacPlate for hard anodizing.
Throughout the development of our CubeSat, we have performed countless analyses. There's been two main branches that I've been working on: the structure in the launch vehicle and the thermal analyses in low Earth orbit. Since I have a relatively deep math background, I've taken charge of a lot of this work. I've been using ANSYS Workbench to perform three main types of analyses: static structural, to see how the satellite deals with the force generated by the launch vehicle; modal analysis, to see if our satellite can potentially vibrate on any destructive frequencies within its dispenser; and finally, random vibration, to find the 3 sigma deflection of components in the structure and board stacks. Mainly, we're just trying to evaluate if any of our circuit board elements have a significant chance to overstress solder joints. One of the first things that I did as part of this team was to validate a thermal model that a previous team member had made of the overall thermal balance of our satellite. Looking forward, I'll perform a transient analysis of the internal temperatures of significant components, like the batteries and torque coils. So far, our analysis of internal temperatures has been on relatively crude radiative equilibria, so we've made tweaks to our design in an effort to increase our margin of safety. For example, I've worked on the design of our magnetorquer rods that we'll use for the detumbling and pointing of our spacecraft. And once we noticed that the magnetorquers produce significant heat when active, we decided to place them close to the battery as an additional heater and thermal body.
When we first started this mission 4 years ago, we knew that deployables would be critical to our mission success. So one of the first things we did was to prototype a burn wire deployment system. On our mission, we have 2 deployable antennas and 1 deployable solar panel. We decided to go with burn wire because it's simpler and more compact and has lots of flight heritage, compared to motors, which are hard to do on a CubeSat since they require a lot more than what a CubeSat can provide. We have 2 tension lines per deployable with 2 resistors for each line to add redundancy. We also have a deployable magnetometer, which is a part of the Z+ solar panel. That allows us to distance it from the magnetorquers and improve accuracy of our magnetic field readings, allowing us to have attitude control and detumble after deployment. As a part of our shooting star dispenser, we have a deployable ribbon, which will allow the student drawings to detach from the satellite to go burn up on reentry. We also could not resist adding a camera, which is on the internal side of our deployable solar panel. This will allow us to take a selfie of our satellite and will allow us to provide pictures of our educational outreach payload, the Shooting Star Dispenser, to those elementary school students who will be super excited to see their drawings in space. We also will take a picture of our CubeSat with Earth in the background.
Hi everyone, I'm going to be discussing some of the avionics systems of our spacecraft. So first, here's a picture of what our board stack is expected to look like in the satellite. So I'll be going over 2 boards. First is the OBC, or onboard computer, that has integrated hardware from PyCubed. The second board I will be discussing is our CPB, or combined payload board, that has a lot of versatile interfaces that can support a variety of payloads. First, onto the OBC. So we based this board off PyCubed. There are 2 main reasons that we chose PyCubed. First, it has flight heritage. The second reason that we chose PyCubed is because it has integration of a lot of the things we are going to want on our board. For example, it is capable of computing, it has radio, GPS, an IMU, and high-power switches. We did make some changes to the OBC. So first, PyCubed is designed for a 1U CubeSat, and our NeonSat is 2U. Because of this, we added an extra solar charging path. So our board now has 2 solar charging paths instead of 1. We also just made some minor component switches because of availability or for manufacturing purposes. The biggest change we made is swapping out the microcontroller. So the previous microcontroller that was on PyCubed was discovered to be more vulnerable to current solar radiation than we had previously assumed. Because of this, we swapped it out for a Raspberry Pi 2350 based on positive radiation testing by Max Holliday. So now for just an overview of all of the systems that our OBC will be running. It will have radio, GPS, IMU, solar and USB charging, burn wire activation, and a new watchdog circuit that we added to prevent latch-ups. Now I will be going into the combined payload board. So the coolest thing about this board is its versatility. So we plan to use it in our mission, but we also hope that it will be used in other missions as well. In fact, we actually plan to use this board for potential future missions that we are considering. So the combined payload board has 8 high-power, high-side switches. It is also capable of pulse width modulation. The CPB also has 8 half-bridge outputs, and along with this, it also has 1 buffered digital to analog converter and 4 analog to digital converters. Another cool thing about the CPB is its adaptive filtering and coupling abilities. So with the same board layout, passives can be switched or removed for different use cases. The CPB also comes with a Raspberry Pi 02W for imaging and camera, and it has a lot of independent subsystems for redundancy. So that's about it for these 2 boards. That's all I'm going to be discussing. We do have a poster track going on upstairs where we are discussing it in more detail. So if any of you have any questions or are interested and have not checked it out already, I highly recommend that you do that.
So since we have these custom boards, to make sure they're ready for space, we need to test each of the components. We did have some challenges in doing so. For example, some of the data sheets haven't always matched the behavior of some components. But despite this, we've just about gotten there, and we have drivers for all the components we'll be using, which will be implemented into the main loop. All the code on OBC is written in CircuitPython, and the CPB's microcontroller will be programmed in C. Our Raspberry Pi 02W on the CCP will be used to handle imaging, and it also includes some file management systems. And of course, all our software will be open source and posted on GitHub. Our telemetry frames will use the AX25 data link layer protocol. And because we're a part of the SatNOGS network, we'll be able to schedule large file transfers through multiple SatNOGS stations. We're also using the JPEG XL format, which will let us downlink small subsets of images that become dynamic thumbnails. So we'll be able to see if we want the image before downloading the entire resolution. So power management is really important for the longevity of our spacecraft. And since we have a lot of power domains and complexity, we need to have a subsystem that will sequence the components to simplify command handling and scheduled actions, as well as to protect the spacecraft and ensure critical systems will stay operational.
To wrap everything up, we're at a really exciting point in our mission. We've completed our preliminary design review, and right now we're focused on implementing that feedback into our critical design review. We're still working with CSLI on solidifying a launch slot, but our anticipated launch will be in spring 2026. Our team has been working across subsystems to finalize designs, prototype key components, and prepare for launch in every way. It's been a huge effort. Every part of the satellite, from the structure to the avionics boards and software, is student-designed and coming together. We've moved out of the conceptual stage and into design and development, and it's been incredibly rewarding to see all of our ideas taking physical form. Most of all, we're really excited to be here, getting to share our work and learn from all of you. Thank you so much for taking the time to hear about our mission, and we've got a few minutes left, so if you have any questions, we would love to answer them. Yes?
Okay, I'm curious. It looks like you have a lot of solar panels, which is good. What's your orbital average power, and how much margin you have, do you have enough margin where if you were to accidentally lose a connection to one of those entire panels, would you still be power positive?
Yeah, so with all of our solar panels, I guess, like, working at once, like, let me restart. So our solar panels are expected to give about at least 2 watts of power. We were expecting more at first, but then once we redid the math, it dropped down a little bit. But since we have a 60 watt-hour battery, we expect that we would be able to fully recover within a couple of orbits for sure.
Any other questions? Yes.
So the question was how we're going to use the SatNogs network to downlink large files. So the way we're doing that is we're going to uplink some commands that will say how much time we want to downlink a portion of the file. So we'll be able to use all those SatNog stations to downlink parts of each file so that we can spend less time downlinking as opposed to just having one station.
Any other questions?
Using acoustic signals as a way of changing, as a way of monitoring the change in the structure is a really economical way to do it. I'm wondering how you arrived at that approach.
Like how we came up with the idea? So the question is how we came up with the idea for the acoustic payload. So we brainstormed when we started this project 4 years ago, kind of what we wanted to achieve with this project and what we wanted to figure out and do. We knew that we wanted to do educational outreach and connect with kids since this was a really great opportunity for us to get hands-on experience. We wanted to share that experience. And with the acoustic payload, we talked about how we wanted to do deployables, but we didn't know exactly how we wanted to decide if those deployables were deployed or not. And we figured out a way with the acoustic that it would be very interesting to figure out a new way, not rely on switches, and use the acoustic payload.
I think you should publish that.
Make sure you check out our poster upstairs. I'm sure there's more information. We can talk about it more up there. Any other questions? Okay, thank you so much.
All right, it's my pleasure to introduce our next speaker, Pablo Iannachi, who's going to be telling us about the preliminary software architecture for an ADCS module in space ROS-enabled nanosatellites. Please welcome Pablo.
Thank you. Good morning. I am very happy to be here in Polycal in San Luis Obispo. It's a big honor for our university to be here. And we are from Universidad Nacional de San Agustín, Arequipa, Peru, and South America. We start to do some preliminary software architecture for ADCS module in space ROS-enabled nanosatellite with our team. Something about us. Instituto de Investigación Astronómico Espacial Pedro Palet y AAPP in UNSA, University of San Agustín, is dedicated to scientific and technological research and training researchers. It manages the Characat Observatorio and develops research projects. It carries out satellite tracking, GPS, GNS observation, DORIS, and scientific dissemination. But that reason, the university asked us to start a CubeSat program because many universities in Peru start to do this program. We are interested in CubeSat also. Our proposal integrates three concepts: ADCS, ROS2, and Space ROS. First, ADCS enables satellite determine and control the orientation using sensors such as gyroscopes and magnetometers, and actuator, light reaction wheel, and magnetorquers. Second, ROST, robot operating system, and is a modular software framework that facilitates communication and coordination among robotic components. And finally, Space ROS is an extension of ROS2 adapted for space mission, emphasizing determinism, safety, and reliability, essential features in aerospace application. The use of ROS in space is not a novel approach. It has been deployed in missions such as Robonaut 2, Astro V, Spheres. More recently, ROS-based frameworks have been integrated into projects like NASA's Valkyrie humanoid and the Perseverance rover. This trajectory inspired our initiative, demonstrating that ROS is capable of adapting to harsh environments while supporting modular and reusable software architecture. In experimental setup, we have developed a test bed that includes a spherical air-bearing platform and ADCS module. The hardware architecture is shown in the figure. A graphical interface was also developed to enable system operation. The experimental platform supports our initial software architecture. This is our preliminary software architecture. It's based on ROS2 and micro-ROS, employing a structural communication module using distributed nodes and topics. These components handle sensor data acquisition, attitude estimation, and actuator control. The system is designed to be modular and scalable, aligning with the constraints and requirements of smart satellite mission. Software architecture under development is the next stage of development. We integrate additional tools such as MATLAB to bridge theoretical and dynamic modeling with real hardware implementation. This approach enables fidelity verification of the dynamic model and the validation of attitude control algorithm in a simulated environment. It's also super parallel development by specialized teams focusing on control algorithms, interface improvement, and other potential applications. The evaluation setup, we defined three performance metrics: message loss, latency, and periodicity, evaluated on a target frequency at 100 Hz. Three different quality or service profiles in ROS were tested. One, message loss, the best effort 2 scenarios, best effort 2 and custom 3 maintain latency under 8 milliseconds and 11 milliseconds respectively. In periodicity, custom 3 showed the highest temporal stability as indicated by the lowest standard deviation among the testbed configuration. As conclusion, we demonstrate that Space ROS is a viable framework for implementing ADCS module in nanosatellite. The proposed as architecture is modular, scalable, and capable of meeting the performance requirement for real-time in-orbit operation. Moreover, the integration of external tools such as MATLAB enhances the platform's flexibility and support interdisciplinary collaboration for future mission development. Oh, thanks.
Thank you very much. That was the last speaker we have, so that's going to conclude the portion of the program for what we're doing here in the main hall. There is a career fair if you signed up for that. So there's a short break now, about a half hour. There'll be some light snacks provided up but closer to the registration booth side. If you sign up for the career fair, please stop over the registration booth side. Again, you go out up the top of the stairs all the way to your right. At 11:45, that's when we'll be giving directions for that. Otherwise, I hope you had a good time, and I hope you'll come back again next year. Putting this whole thing on takes a while, and we end up reserving the dates a long time in advance. So next year we have the facility April 14th to 16th in 2026. So save the date, you can put it on your calendar. There'll be emails and other announcements that come out throughout the year. But I wanted to make sure you had the first notice of anybody. So I hope to see you again next year, and thanks again for coming out this year. Have a great rest of your day.